Okay, I'd like to welcome everybody to the June meeting of the Delaware Astronomical Society. First item, do we have any new members? Like to introduce yourselves, new members? Have me turn it around, yes.
Been about a month, yeah.
Oh, there you go.
There you go. Fixed up. Evening, I'm Andy Rokita. I finally joined DAS after being, everybody's saying finally, after being after being a member of Mount Cuba for quite a few years. So here I am.
Fantastic.
Welcome to fifth year.
Welcome to fifth.
Glad to take your money.
Anyone else? Can you see one more? You've been a member for a little bit. Any other new members? No? All right, so first item on the agenda, just so everybody knows, the new telescope is up in the dome, 52 inches.
No, 50.
50?
Cool.
50 inches.
Yeah, so as the director of Mount Cuba, I just want to say thank you to everybody for, your support and everything else of that nature. We now have the largest telescope on the East Coast.
Cool.
Nice. So Mount Cuba is very unique in that, we're a privately owned observatory and we support astronomical research and we were supporting the University of Delaware. And if anybody wants to use the telescope, you can apply to the board of directors if you have a research project, and maybe we'll approve time on the telescope for you to use. Like I said, this is a very unique instrument, 50 inches, Ritchie Creation F6, I believe it is. It has a very large CCD camera that I have to spend $70,000 or $80,000 for. I have a spectrograph on, a Shellyak one also. It's totally automated. So probably one of the meetings, maybe September, October, when it's, what did you do this summer? I'll give a little talk on, what I did this summer, with the telescope. Like I said, they're not finished with the total installation yet. It's supposed to be done by, I believe, the 21st of June. So we should have unofficial first light coming up soon with the scope. Check it out. But it's finally here after 5 years and COVID and all this other kind of things that's happened. But it's finally here. And again, I'm very, very proud that we're able to accomplish this. You have to understand, when this observatory was built and designed, we had the full power of the DuPont engineering division behind it that actually did a lot of the engineering. That telescope was only 4 of us were involved with making sure that it's pointed north and everything else like that. We didn't dig up an ancient Indian burial ground. We didn't disturb the Hockessin spotted toad. We didn't get sued by our neighbors behind us. We were able to get through the process of all the Newcastle County board for all the certifications. It's officially known as a large electronic shed, if you look it up, because it doesn't have any occupancy, thank God, because if it did, we have all those other problems we'd have. Again, it's a totally automated scope, so you're not even supposed to, you can't even be up in it when it's operating. You shouldn't be around it. Everything will be, we have a control room here to operate it. So, and again, it's any place in the United States or any place around the world actually can control it or use it. So, we hope to do some amazing research with it. I'm hoping before I become worm food that something amazing, we help do some kind of amazing thing. I'm really hoping that somehow we're involved with taking a spectrum of some planet that actually shows there's a possibility of life, and that would, fulfill its goal to actually, help mankind understand where we fit in this universe. So again, a couple more days in first light, but it's here. It's finally here. Thank you.
All right, next on the list, you should note that we have the C-Star telescope now, and we can loan that out to members just like we loan out our other loaner gear. So Note that our loaner gear has expanded, and you can check out our website to see all the different items on there. We have several cameras available for loan. We have some new telescopes available for loan. So please check it out and borrow some stuff. Have some fun with it. Another thing that's very important, we just scheduled the DAS picnic. So the picnic is back by popular demand, and it will be August 3rd. We're going to make this like an evening one. It'll start about 4 p.m. And the idea is then we could transition to observing because it's close to the new moon. So it should be cooler, it should lead nicely into observing, and it should be a very fun time. So put that on your calendars, August 3rd. Please also note that this picnic will be like bring your own food. It's like a potluck. So please bring your own food, no alcoholic beverages, but by all means, please bring other beverages. Bring a thing to share, could be fun. And again, that is August 3rd at 4 p.m.
Grills will be provided.
Oh, yes, grills will be provided. My grill and maybe a couple others, we'll see. Yep,
Where?
here,
Oh, very
right outside. Yeah, absolutely. So the next thing I should point out is that the election was just held, and Sydney can give us some details.
Good evening, everyone, and we all know we just had our elections for the secretary, treasurer, vice president, and president for the next couple of years, and their term will start July 1st. And for secretary, let's congratulate Bill McKibben. Our treasurer, Bob Treblecock. Jeff online, Jeff Lawrence is our vice president. The floor for president, Rob Lancaster. Thank you for your votes, and see you next time.
And thank you very much for running the election.
Oh,
Appreciate it every time.
It's much safer.
Next thing is the Astronomical League. Bob, you want to tell us about that?
Yes, thank you. Couple minutes to talk about the Astronomical League. It runs from July 1st to every year. So we start collecting dues for that now. DAS is a member of the Astronomical League, and since because of that, you're eligible to join the Astronomical League. You don't have to, but if you do want to, it's $9 a year. We get about 15 members that join from the club every year, and we probably have another 15 that are members through other clubs. So we have a fairly large number of people that are in the Astronomical League. So what is the Astronomical League? It's a group of 240 astronomical societies such as DAS, and it's there to promote astronomical education, providing incentives for observing and assisting communications between societies. So that's sort of their goals. One of the things they're known for is their sort of like observing programs which you get a pin for if you earn. So they got about 60 or 70 of them. Various different levels. Some of them are visual, some of them are imaging type things. You go through a series of requirements, and if you complete the requirements, you can get the pin or certificate. So they got a Messier one. They've got outreach things. Those are the most popular, but they have a lot of different other things that are covering a lot of different subjects. So again, it's voluntary. If you want to join, it's $9. You can get a quarterly magazine with that. And so how to join, you can pay at any meeting here or the workshops between now and July 1st. The website has a sign up thing, so with PayPal links and mailing things if you want to mail in payments. So go to the delastro.org website. And the focus, not this latest focus, but the previous focuses also had some links to get that. So if you're interested in joining the Astronomical League, please do that by July 1st, since that's when I send in the money. Thanks.
Very good. Thank you, sir. The next item I should inform you of is currently I'm working on the website. So I've been making some updates and changes to that. You've probably noticed it looks a little different in its format. Should also point out that there's some upcoming events. So just recently, as you know, we held the Bellevue Star Party. That was last Wednesday. On Friday, we were supposed to have the Woodside Creamery event, but that got canceled due to threat of thunderstorms. but we have a number of upcoming ones. Friday Night Lights, Fred's going to talk about in a couple minutes. We have various events in our club with the AP SIG and the book club. Mary will talk about that in a second. There is an outreach at the Museum of Nature and Science coming up in July. So we got a number of interesting events coming up, and please pay attention to the groups.io as people send out invites to ask for members to volunteer. Greg, you wanted to mention
Can
one?
I add to that?
Yeah, please.
Briefly, that Jeff Lawrence has reestablished the connection with the new management at Fair Hill Park. And we are in the process now of working with them to determine which nights that we can use as DAS club, that location as an observing site that we had in the past. It's also a back scratch relationship too, that we help them with some of their public programs. One of which was going to be this Saturday, but got canceled because of the heat extreme. But more to come on Fair Hill as another observing location.
Excellent.
An outreach place.
Yeah. So definitely pay attention, and more info will come out about each of the events as they approach. Bill, you want to talk about the AP SIG?
Yeah, I just want to mention quickly, the next tentative date is July 20th, it's a Saturday, and the announcement will go out over groups.io.
Very nice. And Mary, do you have anything about the book club?
The black area of the state, and I think what you're saying.
Hello,
No,
can you hear me?
Yeah, we hear you now.
Okay. Good evening, everyone. You're all and your guests cordially invited to attend the June meeting of the Delaware Astronomical Society Book Club on Thursday, June 27th at a regular time, 7 p.m. and via Zoom. We're marking the 100th anniversary of Edwin Hubble's reclassification of Andromeda from a nebula to an island universe, a much debated topic at the time, but he was able to finally show photographically and with measurements using Cepheid variables that it indeed was a separate galaxy. It was a monumental discovery, and we hope that it ties in so beautifully to Dave's announcement about a wonderful edition of the largest telescope, because Hubble used the Hooker telescope at Mount Wilson to make his discovery. And so we can see the power of a large telescope and the wonderful opportunity it gives to innovators and people who can have the expertise in astronomy to make discoveries. So we hope that that does happen at Mount Cuba. The book we're going to read is The Day We Found the Universe, and it's the story of Hubble and his discovery. And the writer is Masha Batusiak, who is just an incredible author and academic. She'll be joining us for the meeting, and she's just delightful. David Ives Brown, who is a DAS book club member and also a Rittenhouse Astronomical Society board member, is going to lead our discussion. He's a retired JPL optical engineer, so he's very well qualified to lead this discussion. I think it's a worthwhile book. You can get it through the Delaware Library System via Hoopla on audio. It's the reader is delightful, so you can be working on your telescopes or doing your other projects and listening to this wonderful story. So I hope we'll see you at our meeting, and I thank you. Oh, and just a quick plug for the Library Telescope program. If any of you are interested in participating in the modification of the 36 library telescopes, which will be available to be borrowed via the Delaware Library branches in our state, please reach out and let me, Robert, Jim Kirshen, or Greg Lee know that you can help out with the project. We'll be working on it all summer. We hope to have the telescopes in the branches by the fall. Thank you so much. Good evening.
Thank you very much. Yeah, we actually have had them working at our astronomy workshops with other people working on various projects like every week for the last few weeks. So that's very cool. Do we have any other announcements before Fred's little brief talk? No? Okay. And I'm going to bring up your thing now. Just give me 1 second. I think everybody else is muted. Yeah. Let me close that. No. It should be working, I think. Click that, see that it's just
Good. Well, my, oh my, how time flies. It seems like I just did this about a year ago. And I did. We sit down because I had a shot in my hip and I'm going to give it some rest. Friday Night Lights. How many of us have been to Friday Night Lights in the past? Okay. Guys or girls who've not been there, you're missing a really good time.
Oh, yeah.
Oh, yeah. Here we go. Sydney's. This year, July 12th, excuse me, from 7 to 10 p.m. for the general public, but for the astronomers who volunteer to bring telescopes, you're permitted to bring 2 guests this year. And for each telescope, handler can bring 2 guests. And we need to get there between 5 and 6 p.m. 5:30 is a nice time to get there. 6 o'clock, the gates open up and for the general public. So by June 24th, I'd like to have as many of the volunteers' name as possible so I can submit it to the Natural Land so they can prepare the name tags with the associated club and the names of their guests with the tags. If you want to bring more than 2 guests, the 3rd, 4th, and 5th guest needs to sign up on the Natural Land's website for Friday Night Lights and have to pay their own admission. Our arrival time, as I said, should be between 5 and 6 p.m. so we can avoid the major traffic from the public. It falls the day before the first quarter moon, which sets at 12:04 a.m. that morning. There might be views of Mercury and Venus. I'm not really sure. I did a real quick look before I got here. And but if we can, that'd be great. Other than that, the public loves the moon. And since it's just before first quarter, we should be able to get some deep sky objects in there too. After the event, which ends at 10 o'clock, there'll be an announcement made that the event's over. The telescope handlers should tell anyone who's at the telescope saying we need to shut down because the event's over. But if you plan to stay, just turn your telescope facing the ground or something, cover it up or whatever, and until the crowd leaves. And then we can stay observing for the rest of the night if we like. And since there'll be no moon after 12 o'clock, it should be a decent night if the weather cooperates. 2 guests per astronomer. The location is going to be at the top of the hill, as it was in the past, which is a pretty good location, keeps us away from all the stumbling public. We should have some trash cans and recycling cans there. There's going to be no free beer. In the past, starting last year or the year before, they used to give us each volunteer 2 tickets for free drinks and food. They stopped that, and but there will be non-alcoholic drinks and water at the Natural Land's red tent. No outside alcohol, no food, no dogs. And upon your arrival, look for me, and I can give you your name tag and your guest tags. I asked that all of the guests arrive at the same time as the astronomer. If for any reason the guest cannot arrive at the same time as the astronomer, they'll probably have to park. They should look for a Natural Lands person to be directed where to park, or what they might do is cart them up with a golf cart to bring them up to the telescopes. There's going to be craft beer there, wine, food trucks. East Branch Brewing Company and Animated Brewing Company were there last year. Dressler Estate, I think, is new this year. Brothers Food Truck, Burrito Feliz Philly, Chef and Company, Dia Dolce Cupcakes, and not really sure what Jay's Joint does. Supporting a great cause, as you probably know, Natural Lands is probably one of the largest conservancy outfits in the area. There's thousands of acres of natural land that they maintain, and they're continuing to work on that day in and day out. Walk-in tickets may be available for $55 plus a processing fee. I think if you buy them online, it's $47 plus a processing fee. This is only if the event is not sold out.
But it's pretty much sold out.
Every year it gets sold out. There's usually about 700 to 800 people there. Be live music by Big Takeover and Pawn Shop Roses, who have not heard. You know them? Oh. Some pictures from the previous Friday Night Lights. Always my favorite two-fisted drinker there. We used to bring some pretty big dobs there in the past, but we kind of got away from that because it just got too awkward. With the stumbling public holding drinks and stuff. So I tend to bring a least expensive telescope with me now.
Ladders are not advised.
What's that?
Ladders are not.
Ladders are not, yeah, definitely not, yes. Yep. So this is generally the kind of setup we have since we gave up on the big jobs. Oh, there's a job there, smaller one. It is a rain or shine event, so if you show up, you might get wet. So be prepared to get wet. And matter of fact, Bill Hannigan probably remembers the one we had at the Lenfest Center one year where we were really stomping around through mud most of the night. It was a major thunderstorm just before the event started, and it just turned the area into complete mud. There's an aerial shot. These here are the telescopes, and the car set up, parking, people, band.
We're in a straight line.
Yes, we were. Well, it kind of got crooked towards the end there. Okay, so it's July 12th. Telescope volunteers can bring 2 guests. Email me, fredworld@verizon.net. And so far, I got 14 participants from DAS, Chesmont, and the Chester County Astronomical Society. So whoever else wants to be joining them, email me or grab me during or after the meeting, and I can get you in, get you down.
And if you don't want to take your good scope, you can take the line hours.
I meant to mention that, yes.
We do have loaner scopes
Yes.
for any members. Yeah.
People who don't have a telescope, you can borrow one from the club.
Yep.
And get yourself in free and bring 2 guests if you like. Like it very much.
Yeah.
All right, let me get you guys ready. There you go.
I'd like to welcome Steve Conard. He's going to give us a great talk. In the drawer, I think. Hold on. We did buy one. Hold on.
We gotta ask for one more thing at the last minute.
Yeah, we did buy one.
I'll always do that. So I think the last time I was here was in October of 17. And I gave a similar talk to what Roxanne talked to you guys a couple months ago about on occultation timing. Kind of surprised me because usually I first talk to any group that want to hear about New Horizons. I worked on New Horizons from 2003 till this April. I retired. So I'm a retired optical engineer. You mentioned you had an optical engineer retired from JPL. I'm retired from APL. So don't get them confused. I get upset by that. So I had lived in Maryland. I just moved up to Wellsboro, Pennsylvania, near Cherry Springs 2 years ago. And like I said, I just retired. How many of you do imaging like semi-seriously? You've got a few. Anybody doing spectroscopy at all so far? Solar. Sorry? Solar. Okay. All right, just want to make sure I know my audience. This
I don't think it's working.
does it work?
No battery.
Or can you just put the mouse over?
Yes. You do that.
That'll work. There we go.
I'll give you a nice long extension.
All right. Let's slide to where it needs to be. Got my pointer. Okay, so I think I've been giving this talk. I started it the first time in 2014 or so. But I haven't given it since COVID. So this is the first one I've done in quite a while. I'd like to get some feedback. You guys are one of the more advanced clubs I speak to. You know, there are some pretty casual clubs I talk to, so I try to cover all different levels here. If you get a little bit bored in the beginning, apologies, but there may be one or two of you who maybe this will be helpful. So I'll talk about, you know, what is spectroscopy? What does spectrum tell us? Remember, I'm an engineer, not a scientist. You ask me scientific questions, you get the deer in the headlight look. Spectrometer designs, the more accessible ones for people who may be interested. But the big thing I like to do, and has been very popular with this talk, is to actually demonstrate hardware. So we have an Alfie on the desk here. We have a few light sources that we brought in. I have some of my own light sources, my own filters, and we're going to look at some real-time spectra and think about what's going on with those. People have really enjoyed that over the years. We've had some very interesting light sources. I was telling Rob, the Roanoke folks brought the Jacob's ladder, and we were getting really neat spectra out of that. And we had some people, I'll call older folks, people in my generation, in the front row, and a couple of them started feeling woozy from the ozone really generating from that. So we had to shut down that particular experiment a little early. But it's been a lot of fun over the years. And then, you know, I thought about doing it like the stump the chump type thing, where you put a light up here and you don't show anybody, and we try to figure it out. But that didn't work out well a few times I tried that. So anyway, let's get into it. So my personal history, like I said, I've been an optical engineer for 42 years. Worked for Johns Hopkins the entire time. And my first job when I got out of college was helping with the HUD instrument, which is a 0.9 meter far ultraviolet spectroscope, basically. So it's a parabolic mirror, 0.9 meters, f2, feeding a Roland circle spectrometer. Very first thing I did out of college was put one of those spectrometers together. We put it on a sounding rocket without the telescope, and we sent it up into the upper atmosphere. And we collected the first upper atmosphere spectra of atomic nitrogen. Woohoo! Who would think we'd have nitrogen in our atmosphere? Then we eventually launched that. We were supposed to go on the shuttle after Challenger. And because of Challenger, we didn't get our opportunity to see Higgins' comet. But we launched a few years later once the shuttle program resumed. We flew twice, in 1990 and 1995. That instrument now is hanging in the Smithsonian. I actually was lucky enough to go down to the Smithsonian as the engineer in charge of it to hang it up. So if you ever get down there, you're in the room with the big Hubble mirror and all, look up in the ceiling and you'll see that instrument. Then the second thing I worked with, and like I said, that was a spectrometer working in the far UV, was another far UV spectrometer called Fuse, which was a satellite that we launched in, I think, 99. And we ran for 4 or 5 years before the gyros failed. And we collected very high resolution far ultraviolet spectra. And far ultraviolet light doesn't transmit through the atmosphere. So that's why we had to go up into space to collect that data. So basically my first 20 years was all far ultraviolet spectrometers, which are very simple designs. They're just basically a slit, a grating, and a detector. No optics to collimate or do any of that stuff. Very simple designs, except this was just a spherical grating with straight lines. This was a spherical grating with curved lines, so you can do a lot better resolution-wise. After that, I just did imaging the rest of my career. So I haven't touched these things as a professional in 20-some years. And I guess if I hit the right computer, it would help. Okay, so what's spectroscopy? It's basically taking a sample of something in the sky and saying how much light are you getting in each, I'll call color, for now, going across, so you get more or less of different parts of the band. Now, this is a particularly bad example I have here, and you'll see why later. Is I got ring nebula, but the light from ring nebula isn't going to be a continuous spectrum like that. It's going to be a line spectrum, but we'll see that. Okay, everybody know wavelength? Do I need to go over? That photons are waves. Distance from peak to peak is the wavelength. Shorter wavelengths are more energy. So red photons have longer wavelengths or less energetic than blue. Units of measure. I always enjoy this one because every time I've moved from, when I moved from astrophysics to planetary, the scientists I work with moved from angstroms to nanometers. So angstrom 10 to the minus 10 meters. Planetary scientists, like I said, want to talk in nanometers, 10 to the minus 9. If you go into the thermal infrared, normally talk about microns. And then you run into a real spectroscopy geek if they're wave numbers. And wave numbers are very useful 1 over centimeters, is your wavelength unit. It makes perfect sense if you're a spectroscopist because it makes some math easier. But I believe it's just an evil plot. So this just shows you some of the wavelengths for different colors when you put them in different units. And again, most of the time, if you're dealing with a spectrometer, you're using RSpec as an analysis tool. Typically, you're going to be talking extras. And I've had too much caffeine coming down here today. Electromagnetic spectrum. Everybody remembers we look at this one little area our eyes work over of the whole domain from gamma rays all the way to long wave radio waves. So all we're analyzing is this little area, and you can do spectroscopy over basically anything that's in the light domain. I guess you could even do it in radio domain. So spectrum is your graph. Usually have wavelength on the x-axis. I've got angstrom one here. And the number of photons or the amount of light you're detecting, maybe not necessarily calibrated, so maybe not the number of photons. And this particular one is one of Jupiter that has not been photometrically calibrated. So it's just what my camera puts out the back end in number of counts for each wavelength. But that's generally what you're talking about. You're going to talk about if you're calibrated, uncalibrated, you're always going to calibrate your wavelength, of course. Because if I just had pixel number on the bottom there, that wouldn't mean anything to anybody. So where do the photons come from that we're looking at? So there's thermally, right, black body radiation. So a couple of examples there. You got the blacksmith heating his piece of metal in his hearth and it's glowing, or an incandescent light. They're both sort of black body sources. You also get emission from excited gas. The ring nebula, like I said, is a line source. Your neon light, I think we brought a neon light in. So we'll see that. That's also should be a line source. So there are transitions of the atoms or molecules that are preferential and emit a certain amount of light when they go from one excited state of the electron to a lower. And then there's also just reflected light, right? So I don't care where it came from, but it reflected off of something, and I'm using that reflection to learn something about it. So my example here is a comet, right? Comets don't generate their own light, at least not visible. They might fluoresce, but that's sort of a, it's light coming in, UV coming in, that's fluorescing coming out, or it's just reflecting off the particles. And I just took a picture of Stoll Observatory, and that's my, that's reflected light there. It's all coming from the sun, right? And somebody earlier asked about emission spectra. Was it you or someone else? So emission spectra, so these are, the glowing transitions of all these different lines. Most of them are atomic, that we look at in the visible. So you can identify what you're looking at, the gas you're looking at, sort of like a fingerprint, right? So each wavelength is, or pattern of wavelengths is generally unique to whatever gas or you're looking at that's either fluorescing, glowing, discharge, whatever. And then the absorption lines are basically the opposite. So if you take a continuous wavelengths of light, you pass it through a gas, then the gas is going to absorb that radiation and possibly re-radiate it in different directions. So you lose light in those wavelengths. And that's what you're seeing here. This is a Neptune spectrum, the absorption lines of hydrogen there, ammonia, methane. So did that answer your question from earlier or?
No,
Okay,
so it's passing through a gas. Talking about what?
The absorption lines-
gases there, right?
the absorption lines are passing through that, in the case of Neptune, a couple of different types of gas in Neptune's atmosphere. Before, so imagine continuous solar radiation. Yeah, there's a few absorption lines that in the sunlight in that wavelength. But imagine that hitting Neptune, going through, I'm hesitant to say Neptune's atmosphere, but going through some gas, hitting whatever on Neptune, and then going back through the gas again, then going to Earth. So it goes through the atmosphere twice and loses light at those wavelengths as it passes through.
Okay.
So you can also, there's a lot going on, right? Because you also have just scattered light. So that's going to be, it's going to have a wavelength dependence, but it's not going to have, generally not going to have features like that. So when you have features like that, you can identify the gas. So I think it was Titan. So Jupiter's moon, Saturn's moon Titan, where the Dragonfly mission's going. I think it was Kuiper at University of Arizona in the late 40s, who discovered the atmosphere there by finding absorption lines in the spectrum of Titan. Any other questions?
So how does dips correlate on the, at the bottom?
What do you hear? So each of them corresponds to a wavelength or a range of wavelengths. So that's 6,000. Yeah. So there's like one at 6,200 angstroms. There's one at 6,600 angstroms. So a scientist on the ground would have basically a catalog of different wavelengths and gases. And they would look for where are the valleys, what are the widths and things like that. And say, oh, well, okay, if you have one here, at 6,200 and one at 6,700, that pair is generally methane. And you say, okay, so I know that there's methane on Neptune, which there is certainly. In fact, a lot of you do oftentimes when we do our occultations involving the moons of Neptune, for example, which is, I guess, the big one is Triton, which has an atmosphere, I think, as opposed to Titan on Saturn. When we do that one, oftentimes we'll want to put a methane filter on to knock down the light of Neptune, so Neptune doesn't dwarf the light from the satellite that's occulting a star. So we'll take advantage of the fact that Neptune looks darker in methane light than the moon would, and not a moon without an atmosphere. And it boosts our ratio up so we get more contrast. But I'm getting more time. But I think I'm going to come back a little more on absorption lines, addition lines. So if you have anything more come up later.
Subtle terminology thing, there would be, their molecules would be in a band, not a line. There's a lot of, well, background of that. But if atoms have emission lines and absorption lines, but molecules are bands.
Okay.
Yeah.
Scientist?
Yeah, I'm a atomic spectroscopist, actually.
But, I will sit down now. All right, so the simplest thing I think that something like a stellar spectrum can tell you is just the temperature. So this was done, I think I did this in RSpec, where I took the spectrum of Vega, which is a bright white star, and you can get the spectrum and then you can compare it to a reference spectrum. So there's Vega is the red, and the light blue, can you see that? It's a little hard to see. You should have up the gain on that one a little bit. There's 4,000 kelvins, 5,000. You can see the peak here versus there, getting closer at 5,000. 6,000 here, 7,000 there. So you can estimate the temperature using that. Now, I don't have I think these are uncalibrated. In fact, they have to be because they don't match exactly. So not photometrically calibrated. So these aren't going to be exact until you do that calibration, but you can see how you can roughly match temperatures by doing that. And then you can match your absorption lines in the spectrum. And again, this was with RSpec. And RSpec, you can tell it, oh, put methane bands in, put the argon lines, calcium lines, hydrogen lines, and you can try to match sort of like what they call the fingerprint, right? Where, doesn't match. Now, there's one that happens to overlap. Another one that's close, doesn't match at all, but then you put the hydrogen in, you get the Balmer alpha, beta, etc., and they all match exactly. So that's how you can identify your chemicals easily if you use RSpec as an example. I'll talk about software in a while. Some other things you can get. You can measure velocities if you have a high resolution spectrometer. I love this one. So this is Jupiter with the slit going across Jupiter. Again, a high resolution spectrometer. And you notice how some of the absorption lines are slanted and some of them are straight. So if I can ask you not to answer, can anybody tell me why some are straight and some are slanted? Or let's start easier. Why are some slanted?
Rotation of Jupiter.
Right.
Top of
So why are other ones straight?
They're not moving. They're not moving.
Well, why? I
Maybe
mean, you're
they're
right.
in a very
Why?
specific spot. Maybe they're in poles, maybe they're like a part that doesn't move, maybe.
So the slit, the Jupiter's like this, with poles up there, the slit was across the middle of Jupiter. Sideways like that.
So it can include the moons, or it can include?
No, it's just Jupiter.
Just Jupiter.
What's the light source? Is it the sun?
Yes.
Did they respect the lines of the sun?
No.
No,
But, well,
so that's been
I shouldn't
subtracted.
say that. I can't say that for sure, but most of them aren't.
Okay.
So what goes on once the light gets back to us?
Oh.
It goes through our atmosphere. Sure. So our atmosphere, they're straight. In Jupiter, they're slanted. Anyway, I just love it. So I don't think I've ever gotten anybody who got that right away from me. And then you can see, you really want to see the shift. You can take spectra 3C273, which is, I think, one of the brightest quasars. And actually, my very first scientist I worked for at the university flew a sounding rocket to this, to see this, and got a spectrum in the ultraviolet showing the Lyman alpha shift of this particular quasar. And he got some prestigious Young Scientist Award at the time for doing that. So it's a bright one. It's available. You guys, you have a spectrometer now for your big telescope. This would be very low hanging fruit for you guys to do. It's not new science, but it's good stuff. And there are plenty of other quasars within the reach of a 50-inch telescope and a match spectrometer. So I envy you. So other properties, right? You can do, if you get high enough spectral resolution, you can measure things like pressure and temperature line widths, type of excitation, fluorescences, all sorts of different ways to measure temperature. It can get really extremely complicated, correct? To deconvolve some of the more complicated spectrum. Okay, so spectrometers. So basically, again, all you're doing is you're measuring for each wavelength of light, count how many photons you got over how much time, and plot it. So that's what I'm trying to represent there. So you sort of have spectrometers in your everyday life. You don't have very high resolution ones, and maybe people would object to the term spectrometer, but your eye sees multiple wavelengths. So your eye can tell you how bright what you perceive as blue is versus what you perceive as green, etc. Your cell phone camera, right, has their filter matrix on it. So it's measuring 3 different color bands when it does that. So you can think of those as simple spectrometers. And then what we're going to do now is we're going to have a first demo. So this is a handheld spectrometer. The Seconic C7000 industrial spectrometer. This is calibrated. So it gives you units of milliwatts per square meter per nanometer. So it's calibrated across the band. I'm going to pass this around. You want to take your own spectrum. If you have a filter or a small light source in your pocket, this is the input. So put your light on there, and then the single button on the right-hand side, if you push it, if it's a faint light source, it's going to take a minute to come out. If it's a bright one, it won't. So let's use this for one demo. By the way, what I have this for, why do I have this? We're trying to work on light pollution prevention in the Pennsylvania wilds. As you guys know, I'm very, very near Cherry Springs. We are in an area that is kind of adverse to regulations. So we're going around basically trying to demonstrate why certain types of lights are bad, amounts of light, things of this sort. I think everybody knows here that blue light is much worse for the night sky than red. Depending on which wavelength you pick, it's about a factor of 7 worse. It's scattering and how much comes back down. But what I also found this was good for is also we do a lot of outreach and stuff with kids and all, and letting kids see immediate feedback and see what spectrum is. It's just really nice to have. And one thing I found in here when we were playing around before most people got here was your lights you have in here. One of them's different. Which one? If you were here for that conversation, don't. don't say. What do we got, 5? No, I'm not counting the exit sign either. So the front one, so what do you think's different?
It looks different to me. There's more red.
Yeah, and that's actually true, so. We take one of these. It'd be hard to see, but there's a continuum spectrum, and then there's also a peak in the blue. So that's a typical LED nowadays, right? So what most LEDs do is they have a blue LED and they put a phosphor in front of them and down convert. You get the sort of pseudo continuum on the low end. Problem is a lot of them, they don't put a very good phosphor on. The phosphors decay. Did you guys get the purple street lights around here like we had in Maryland that went bad? Which are just horrendous. So how well you convert that blue, get rid of the blue, is an issue. So anyway, trust me, but those 4 are LEDs, basically measure the same. And then when we do this one, CFL. It's your typical fluorescent. It's a CFL. I probably have one left over from the old days. That's the one. One up front and one a little bit different. I'm impressed you guys picked that out because I just assumed when I came in they were all the same.
There you go.
And let's hit this one again so they can see that. So I didn't show that. Okay. All right, so I will pass this around, and if, like I said, if you want to put a filter in front of it or you have a dim light source, go ahead and do that. It's the button on the right, and you'll probably pass it around fast enough. It won't turn off with the timeouts. Oh, okay. Did I cover everything on there? Yeah. Oh, yeah. The one thing I do is for the kids, I do a pseudo demonstration of sunscreen. It doesn't go down low enough to get the UV light that sunscreen really cuts out. So I just use filters in this place and show what the filters effectively is.
This is accounting for 7,000 costs.
You want to know? $2,700. And then you really need to keep it in calibration. And see, if I'm going to get in an argument with someone over street lights, I need to have calibration, or else they're just going to shoot me down. Okay, how spectrometers work. Simple spectrometer could just have filters. Each filter has a different bandpass. Prisms. Everybody's probably played with prisms in their lives. Diffraction gratings. So similar to the star analyzer, which we'll pass around in a minute. It's just a diffraction, transmission diffraction grating. So hold it up to the light, look above and below, and you'll see many orders of spectra. You're going to see that one side above, I'm not sure where I'm holding it, looks much brighter than below. That's the blaze of the grating. That's how they made the grating to maximize the efficiency. So basically, a diffraction grating is just a series of lines that do constructive interference, either transmitting light or reflecting the light, depending on which type you have. And then the last example, bottom right there, is a prism. So that's a grating on a prism. And there's advantages to optical design doing it that way. The Alpine 7600 here is a prism spectrometer. So it has a prism with a grating on it, basically. For this particular design, the main advantage is it produces a straight through light path rather than an angled light path. So spectrometer properties, typically, most amateur ones will have a slit. You can also have a pinhole. You can also be slitless, like the star analyzers are. And you'll get a spectrum of the slit going across your target, and it will either have spatial resolution or it won't. The ALPI does, which means that I can do a measurement across ring nebula, and you can see, that there's the top of the ring and the bottom of the ring, and I don't know if I just happened to catch the star in the middle or not. Idea. Okay, Star Analyzer 100. There's also the 200 version. 100 and the 200 refer to rough spectral resolution. That's how far apart you can break up your wavelengths. So all you do with that is you have a telescope that is refracting or reflecting light down onto your film, CMOS, eyepiece, whatever, and you just put a grating close to the usually your camera, and you just get a diffracted image off to one side or the other. You'll actually get them on both sides, but the first order one is going to be brightest. You'll also get the direct image still from the star. That's what the white light is showing there. The problem you have with this is you don't have a slit. You can't get rid of the background light. So you're really limited by how much background light you have. Being at a dark sky site really helps you with these, where a slitted spectrometer makes less difference. There's a picture of the Star Analyzer. It's basically just on a 1.25" filter mount. Again, it works best with point sources. If you use it on an extended source, you'll get an extended image of the spectrum overlapping itself. So it's not really useful for large extended sources. So we'll pass this around. I'm going to pass it around like this. If you're confident in your ability to handle optics, please feel free to pick it up and look through it at your light. And if you're not, don't. So that's the real good beginner's point there. Here's what one of the spectra look like. Again, here's ring nebula. So you have the direct image. This is what they call zero order. And then your O3 line and your H alpha lines out here. And you can just barely see it, but here's your O3 again right here at the minus first order. And if you went down even further, it's probably right in there, maybe. It is the second order. So you'll always get those, but they'll be much fainter because of the way they designed the gradient. So again, you see you have all the overlaps. You can also look at it as, well, I get a whole bunch of spectra for the price of one. And, so if you can get around the fact that you're going to have some overlaps and things of that sort, you might be able to find some really interesting stuff.
That's true.
So the advantages is what I would consider an extremely low price point for getting started. I think it's about $180 for the 100 right now, but I purchased mine a long time ago. Finding targets and tracking is really simple. You have this big field of view. You typically, you can just do tracking like you've done on any other telescope image over time. You can put it in a filter wheel and allow a quick reconfiguration if you want to. And there's almost nothing to adjust or align. You can change the rotation by spinning it in its mount. Disadvantages is the low spectral resolution, limits the scientific usefulness. So like I said, you'll get about 1 part in 100 resolution. point source or emission line sources only. You saw the way the Ring Nebula was split up. Since it was a line source, it didn't matter as much. It was an extended source. It is very, very sensitive to sky brightness, low limiting magnitude. And you need to make sure that you're not overlapping spectra with other spectra, zero orders, etc., in order to get good data out of it. But I really think it's a great way to start if you've never done this before. You just want to dip your toe in and see if you like it at all. Next, generic slit spectrometer. Again, you start out with the collecting optic, your telescope, mirror, lens, whatever. But then you go through a slit, which is a key difference. So you're only letting in a narrow line of whatever your target is. You then put that typically through a collimating mirror or a collimating lens, and then your dispersing element, what breaks it into the different colors. And then you refocus that down onto a camera typically, or an eyepiece, I guess. So that limits the background light and also tells you exactly where you're pointing. It makes tracking harder. So that's a big downside to me, is learning how to guide and keep your light down the slit. And your slit has to be matched to your telescope. So the big criticism I have of my Alpi is I've now used it almost exclusively on my C14, which is too large of a telescope for the slit size. If I go and put a larger slit in so I can get more of the light from the C14's diffraction spot, and the fact that the East Coast seeing is what, 2 to 3 arc seconds, something like that. So I could open that slit up to get more light through. If I do that, I get lower spectral resolution. So it's a complicated trade, and you have to understand whichever spectrometer you're buying is matched to a certain focal length and F number. And you need to ask those questions before you buy. So here's what the Alpi 600 in its current incantation looks like. I think it's pretty funny. I'm already on the third camera on the back of it, and the second guide camera, and soon to be the third because my old ADEC 314 is dying. So that's going to have to be replaced soon. So basically, what you got is the 2-inch telescope interfaces here. Since I'm running on a C14 at f11, I use a 6.6 or 0.66 reducer. The Alpi is good to about f5 before it gets overfilled. You'd never want to overfill spectrometers because you get huge amounts of scattered light when you do that. That light goes through the calibration module, and what that has is a motor and a flap that puts a block in the way of the light path, and then has 2 different lamps. It has a tungsten lamp that gives you a pseudo continuum, I guess, and it has a mercury neon argon source, if I remember right, in there to give you wavelengths for calibration. And here you have the guiding module, and the spectrometer itself is actually in this tube right here. So the light comes through there, hits the slit that's here. That light that doesn't go down the slit is reflected to another mirror here, another mirror over here, and re-imaged onto the guiding camera. So when I run this, you're going to see the slit. I get an image of the slit through this camera, and I can see what the target is that I'm putting into the slit. So that's a big deal. Oftentimes, well, I shouldn't say oftentimes, if you get the very basic Alpi, it doesn't have that. And then it's like, how do I know what light I'm getting in my system? Then that light gets focused into the camera, and I just recently changed the camera because there's now CMOS that has large pixels. And the Alpi is basically matched ideally to about a 10 micron pixel. And if you can get a pixel that's close to that, then for very low signal levels, your read noise really makes a difference. And you'll get more signal on a single pixel with CMOS, because CMOS can't really bin the way LCCDs could and take advantage of the lower read noise. So anyway, this Player One camera just came out recently, is a cool 9-micron pixel camera. So if anybody's ever looking for big pixel cameras, that's your real good choice right now. Yeah. Oh, one other thing I did recently that really made my life easier is, since I go back and forth a lot with my C14 between doing occultation timing and doing spectroscopy, I found that I would be hesitant to switch out of occultation mode because of how long it took me to switch the two cameras over. And what I finally figured out, you think, geez, an engineer with 40 years experience would figure this out a long time ago, is dedicating a permanent wire harness to it. So this wire harness now is all dressed out, is perfectly the right length to go to my power and USB hub that's mounted to the telescope. So when I change it off, now rather than taking an hour or so, literally I can make the change in 5 to 10 minutes. So that's been a huge deal, and like I should have done that many years ago. So here are some ALPI 600 images again, M57. The camera image there, the ALPI image, what comes out of your spectrometer looks like what's up above. And then I zoomed in and just pointed out some of the lines you get from it. Venus spectrum, that's reflected light with absorption lines. So there's a bunch of extra absorption lines in here. I think that's for oxygen atmosphere. One of my favorites is doing this for public outreach, is to do alberio A and B at the same time. So double star, I'm sure everybody knows, one's sort of bluish, one's sort of golden. And if you orient your split so you get both of them at the same time, you can show both spectra at the same time. But you can see the shift with B being hotter, so it's bluer, more towards the left, and A being more like our own sun, or about that temperature. So everybody, I'm sure, is aware of a blaze star, which we're expecting to go off. And please don't tell me it went off tonight, because I won't be able to get back to my spectrometer for a week and I'll miss the whole thing. But of course, we're expecting the recurrent nova to happen sometime this summer, or by September, I think. And I'm sure almost everybody who's thinks they're an amateur spectroscopist is taking their pre-images of the blaze star right now. I've gone out several images, several evenings, and done them. And we're all dreaming that we're pointing there while it goes off, right? And instantly we're the co-authors of some paper. But I think most of us will be happy if we just get a before, during, and after as it decays spectrum. So this is what one of my calibrated spectra look like. So I've photometrically calibrated it. And the way you do that is you go to a reference star that's nearby. So you go, and there's actually one of the stars in Corona is one of the which catalog it is, doesn't matter. One of the star catalogs of a stable star with a published spectrum. Take data there, then you go to your target, you take data there, and then you use the reference one to calibrate the response of your spectrometer. Put that into your data you got from the nova, and you get a calibrated spectrum out of it. A little skeptical on each end because my signal levels are not as good there. But the middle is probably fairly good. Hopefully I'm going to a conference this weekend with a bunch of spectroscopy people, and hopefully we'll have theirs there. We can compare and see how mine will compare to theirs. Okay, so Because I have a lot of experience working out the 600. Here's what I think my advantages and disadvantages are. So it's modular. So the way you get the alpha is you can buy the spectrometer part of it, but no calibration module, no guiding module. And then you can add to it. You know, as you get a little more money here and there, you can buy those things. My feeling is, even though that's true, you can't really do much with it until you get those other things. Maybe the cal module you can do without. If you want to, you know, have a line source or something, you can calibrate it with yourself. It does have a true, what I call slit jaw camera, is what we called them in the old days, so you get to see what you're putting in your slit. And that just makes knowing you're on your target and guiding on them much easier. That's calibration sources. Resolution, I typically see something around 500 going across, which is a fairly good compromise. I think most scientists would say that's low resolution spectra. But since I like to see like what chemicals are coming out of comets and stuff like that, it does what I need it to do. You can use your old cameras as sensors, like you see my ADIC 314, I think is 15 years old, is on there. And until recently, it was working as a fine guiding camera. And it also had a couple of other cameras on the other side of it for a long time. It really also has really good spatial resolution across it. And if you're looking at extended sources, you can collect a lot of data really quick with an extended source that has changes over its surface. Disadvantage is really when you get everything on it, it does get pricey. You know, it's at least 3K plus whatever cameras you have on it. So again, you can use possibly, if you have older retired cameras and imaging, you might be able to take advantage of some of those. The mechanical interfaces aren't really good stability-wise, and you really want a stable spectrometer so you can calibrate it and then point somewhere else and not worry about things shifting. That is not perfect in that regard. I'm thinking about actually machining a cage for it to hold everything together tight. Again, it takes time to pull on and off your telescope compared to like a star analyzer, but you do a harness like that and some other tricks, you can make that time better. Again, the narrow slit, so 23 micron slit on this, is matched to a typical 8-inch telescope. So when I run it on my C14, I'm losing light. I'm not getting light down the slit. I do have what's called a photometric slit on there, which is a step slit, and it has a 1/4 millimeter section where I can put my target in and know I'm collecting all the photons at lower resolution. So there's a trade-off there. So you always, again, you need to match your spectrometer to the telescope and what you're trying to observe.
You can't stop down the objective.
Well, the problem is East Coast seeing is your focal length, right? So your focal length saying how big is that star image at the slit. And with a C14, it's quite a bit larger than a 23 micron slit. So I am thinking about making my homebrew one better matched to my C14 at some point.
So it's a matter of focal length, not aperture.
Well, the aperture is limited by what cone can your spectrometer take. So you don't want to overfill. So ideally, you go as wide as you can go without overfilling and stop there.
So what's the F number on the spectrometer?
F5. So if you go faster than F5, you're going to have a lot of straight line issues. And some of them, other spectrometers faster and slower. So again, you need to make sure that your system, look at it as a system issue with everything you're doing. And I do have experience with one other spectrometer, Starlight Express spectrometer. I've gotten to use these at work. This particular model was discontinued, but the Pro model looks very similar, except they've motorized some interfaces on it. Typically, what you do on this one is you shift your camera left or right and refocus depending on what wavelength range you want to cover. if you go to you can say, oh, wow, I have a really big sensor that I can put on there, a real big chip. The problem then you have is it's got a curved focal plane, so it'll start going out of focus at the ends or the middle, depending on what focus you pick. So again, my experience on this, it's higher resolution than the Alfie. It's almost a factor of 3 higher. It does have a built-in calibration source. You get this, it has everything, right? So it's one purchase, it isn't modular like the Alfie. It is very mechanically stable. It doesn't go anywhere. I love that with it. Spatial resolution for extended sources isn't real good and varies by wavelength. Where the Alfie basically is the same spatial resolution along the slit at any wavelength. This starts smearing at the ends. And again, you have to translate focus camera at every wavelength change. But you can automate that with the new one with the motors, do it with remote operation. I think the latest price I saw for the newest one with the motor is $4,700. Again, time to take a lot of it off the telescope, but I think it's wiring harness is simpler than the Alfie, so you can make a real simple harness for that. Again, it has a very narrow slit, 20 micron slit, matched to an 8-inch telescope. You can go to a larger slit. It does have changeable slits in it. If you do that, then of course you're lowering the resolution. So your R1500 is going to drop. And it doesn't have a true slit jaw camera. You're not really looking at the slit. There's a prism beam splitter before it, 90-10. So you throw away 10% of your light and directing it into your guiding camera, which is built in. You don't have to buy the guiding camera. But you map where the slit is onto your chip and you hope nothing moves. And again, it's a very stable system. I haven't seen a problem with that, but it is to be somewhat of a compromise. Okay, data processing. A lot of similarities to what an imager would do. So when you're collecting data, that's the list of everything you need to collect on the left side there. So you take your biases, your darks. I put quotes around the flats because the flats we take aren't what you imagers would normally call a flat. It's basically, I think the way they try to use it is along the spatial direction and do basically a one-dimensional flat across there. You need to take wavelength calibration images. You need to take your sky background. If you have a long slit and you have a small source, you get that naturally. You need to take a reference star if you're photometric and calibrating it. You need to take your target. So oftentimes when I'm doing it, it takes me like 4 times longer to take all that I need to take than to just take the target's data. But I'm slow, so maybe a faster person. And I also don't trust things, so I repeat things a lot. So it's a big process. If you use an integrated software package like the Metra, it walks you through it. So it reminds you to take everything and gives you a red light, green light chart telling you what you've done and haven't done. Biases and darks are pretty similar to what imagers are used to. Like I said, flats are sort of one-dimensional for localized issues. Sky background subtracted. Wavelength calc converts pixels to nanometers, angstroms, whatever you're using, and your reference star calculates your response. Software, there's a whole bunch of different software packages around. RSpec's probably the most famous one. If you get a star analyzer, you'll probably get RSpec. I get Tom Fields, the guy who wrote that. And he used to be at NEAF and things like that, but I haven't seen him the last few years, though I know he's still selling the product. Shellyak has ISIS, rather unfortunately named software package. And they also have Demetra, which is what I use, that are specific to spectrometers and sort of written mainly for their spectrometers. You might be able to get them to work with others. Or you can collect data with your favorite imaging program, processing through ISIS, Demetra, RSpec, somewhat as well. And I still have a lot of friends who use, believe it or not, Excel or MATLAB and do their own processing in routines they've written. Demetra and ISIS are both free. I really like Demetra because it's end to end and walks me through what I need to do because I tend to get stupid at 2 in the morning. It's less powerful than ISIS, but ISIS makes my head explode. It's so complicated. And then for demos like this, I use RSpec because it has a really nice display that nothing really is. Just some other random notes. Guiding on slit spectrometers can be a challenge. Your slit jaw camera typically has a really small field of view. Most guiding software doesn't let you put images in a slit and keep them there. The two I know that do are Prism, which is a very expensive observatory program, and PhD Guide that have tools to do that if you want to go down that path. I'm still trying to work on that with the Sky. That's what I use for those for guiding. For low elevation targets, you need to keep your slit vertical to the horizon so you don't have atmospheric dispersion influencing your data. So that's, you know, if you're below 30, 40 degrees above the horizon, you need to consider that. If you're working with a wide spectral band, you know, you have to worry about second order contamination. So if you're going from 3,500 to 8,500, you're going to need a second order rejection filter that you can pop in. You'll be working with resolved objects or pushing faint limits. You really need good spatial resolution. You'll get higher sensitivity with those. And we all like to have high sensitivity instruments. There's a type of spectrometer called Michelle that can get you super high resolution. And I really want one, but there's very little I can do with it because that high resolution limits your limiting magnitude a lot. So if I wanted to do bright B stars, for example, a Michelle might be a good idea, but I might be limited to second or third magnitude. So know your expected targets before you pick your spectrometer. Again, I've mentioned this a couple of times, slitted spectrometer is usually designed for specific F numbers and aperture limits, overfilling, lost light, scattered light, too long a focal length, you end up with small fraction light getting through your slit. And like I was mentioning with the big pixel camera, you want to match your spectral camera's pixel size to your resolution, your spectral and spatial resolution. And that's why I ended up buying a big pixel device, which, you know, like 9 microns is big pixel. There's 20 or 25 microns is big pixel. You know, CCD. So amateur science, there are a lot of pro-am opportunities, or a fair number out there. Long-term monitoring of variable stars and decaying nova. AAVSO has a program where you can submit spectra to them. They want those. Collection of comet spectra, frequent sampling. Comets often change how they behave as they get closer and further from the sun. The bright comet we had during COVID, I don't know what the name of it was. That one I collected spectra of, and initially I was getting a big sodium line, and that sodium line disappeared. So it was kind of neat seeing the thing evolve as it was backing away from the sun again. And I know the folks on the Dragonfly mission are looking for people to monitor Titan's atmosphere. And the reason why I talk about doing things like this and also monitoring B stars, for example, is the professional astronomers, especially, they always joke about the bright stars. You can't get money to observe bright stars. So having people on the ground being able to do good spectroscopy and look at the same object for a long period of time, very advantageous. Scientists are always looking for opportunities like that. some organizations, and some variable star people, they collect spectra of variable star parameters. Alpo collects solar system spectra parameters. And they don't get a lot, and I think they'd really like to get more. So there's an opportunity there. SAS, just a quick poll. How many people know what SAS is?
Are we talking about the Society for Applied Spectroscopy or something else?
No. So Society for Astronomical Sciences, which is really the group that claims to not control, lead pro-am stuff for science with small telescopes. This weekend, they're meeting out in California, which I'm going to. I'm going to PWI and flying out first thing tomorrow morning to go to that conference. And they have a whole bunch of members who are involved in making their own spectrometers and using them, and a whole bunch of presentations at this conference about using spectrometers on small telescopes. So if your group, I think they would still consider your 50-inch telescope small because you're a small group. They'd certainly be interested in hearing from you guys. If you guys start collecting data, you might want to think about having some of your folks go to that. It's a great conference to meet people, talk about stuff. Usually a lot of interesting papers, though. There's always one or two you shake your head about, but I guess you get that at every conference. But they do that both in person and in Zoom. For me, it's much more important to go in person and talk to people face to face. Okay, so we'll do a demonstration now. Is it really 9:30? Yes. Yes. Oh, gosh, I'm sorry. I didn't realize we were running anywhere near the sleep. Okay, so let's see if we can do some stuff quick. What time do you guys shut down?
There's not really a time, but.
Again, I apologize. Normally I go for an hour.
Yeah.
Okay.
Well, it's just enough good.
No, I'm not saying that. Okay, so what we'll do is we'll switch the monitor, the display to my computer. Okay. And we'll see what we can do.
Try that. There you go.
Yeah. So this is our spec display. So this is the image our spec's using. It's analyzing the data between the two brown lines. And it's plotting an uncalibrated, unphotometrically calibrated spectrum, though it is always uncalibrated. And then go on and just gives you an idea of what colors are what if you don't want to try to remember what angstroms are what. And I'm feeding that by using SharpCat in this case. So this is the SharpCat image. So what our spec's doing is when I capture an image on SharpCat and gets saved, our spec's going out to that directory looking for whatever the newest file is. And it's just going to process whatever the new file is and put it up there quickly. I do have the guiding camera on. So this is an image of the slit. I'm not patient enough. One of my many good progress. Okay, so there's your slit. I don't get it too bright. So the narrow slit at the bottom, the long narrow part, that's the 23 micron one. Then above it is the 1/4 millimeter slit that is for getting all the starlight in. So that's your photometric slit. That's an option on the Alpi. The standard one just comes with a 23 micron straight slit. That's the whole length that you see up there. So I think we'll not probably look at that anymore. Okay, so let's look at This is, actually found this the other day, an old traditional flashlight with a regular bulb in it, the old school one, the ones that are getting rare now. So we got all those lights out. Hopefully that doesn't happen this much. So all I'm gonna do is put enough light, so I'm not saturated with this area here is the narrow slit. This is the wide slit. The wide slit's getting more than 10 times more light through it. It's so much wider. So that's what we're going to concentrate on, the area where the pointer is right now. Gonna take a snapshot. Okay. I don't have the light up there anymore. We'll go back to our spec. There you go. So there's your spectrum and R spec. An interesting little step there. Not sure why that's there. You see that in the blue? I'm not sure why that's there, but otherwise it looks pretty much what I expect. Now let's put an LED on it. This one's probably going to be way too bright. There you go. So what's that? What's telling us? What is that telling us about this wonderful flashlight?
Blue.
That's really blue.
It's most.
So if I was lighting up my whole parking lot with this would be really, really bad.
But it's probably color balanced to the human eye. You've got a pretty narrow blue area and a much broader green area, broad red. So does it look like to you when you aim it at something?
Yeah.
It's a little bit like the whiteboard. You know, try the whiteboard. See, so they did that so that it would look like a white line.
So where's the other spectrometer? Good. All right. Everybody know what color temperature is? So this is the old guess the color temperature game. So your lights up there at color temperatures of 3000 kelvins, which is your warm light you get at home. So let's put this on and see what we get. 4400. So not quite as bad as the county parking lot in my county's 5000 Kelvin lights. And that's a sore point. And I would say, yeah, they're comparable. So this is probably on 44, 45, 100 kelvins. All right, let's try, how about my blue laser? Yeah. Kind of boring, but what you expect.
Yep. That would have shocked people and made me wonder. Actually, this would shock them more.
Yeah. All the green. That match set of lasers I have for, again, doing demonstrations. Kids, for the most part.
Shouldn't there be one at like 1100? Because it's a doubling it's used to make that work.
Well, I coverage only goes up to
Oh,
7,800.
Never mind. Got it.
But if you want to buy me one that goes up that high.
Okay.
Oh, yeah.
Because the green ones usually use a frequency doubler.
Sorry about this. I'm really bad left-handed. They don't behave basically like you expect they would. All right, do you want to try any guest light sources?
Yeah, well,
You're ready.
Well, this is just LED.
you gotta just plug it in. You got a socket to plug them with.
Oh, there's a strip right down there.
That's good.
Yeah, I think you should. I'll tell you, hang on. Okay, that's good. Just hang there. Okay, got it. You can put it down. There you go.
That's a nice.
All kinds of lines.
So you can imagine how you can ID it with that pattern, right? Oh, let's take a look at the cal source on spectrometer.
Should be pretty close to that.
So here's the cal lamp, and you can see that, you know, most of the big lines are up here in the red and near IR. Get some down here, but there are ones here that actually are very measurable. So you can get your cal. I think my lowest cal line I can measure is like a 39 change, something like that. And since I only cover 38 to 78, with the way I have it set up right now, basically I have enough calibration lines across the whole thing. The only thing challenging about the built-in cal lamp is if you're doing your own calibration, which I think everybody needs to do once or twice in their lives, you have to realize that different calibration lamps have different lines of different heights, or the same lines of different heights. So you might get a printout from the vendor showing you that, oh, there's 3 big lines here and 2 smaller ones there. You almost have to ignore the heights. Usually your own lamp, I found, stays fairly consistent. So once you get a good one that you calibrate it, take a printout of it, put it somewhere safe, and save it in 4 places on your computer. And then we'll put the flat on, which I might have to shorten the exposure. Yeah. So you can see it's just a more or less continuous black body light spectrum. All right, other guest spectra. That looks pretty white.
Yeah.
Give it a shot.
Why not?
This ain't the other one. I'm not get it.
Or maybe. There's some fun.
Oh, I just, I never put the exposure time back up. That I can control. Oh. God. So if you leave the flag on, you have a paddle in the way, walking the lake path. There we go, that looks more believable.
Classic.
Cute. Anyone else? One of that one. Just point it out right there. Doing light first. This is much easier now that I go two hands. Probably gonna look very much, it's even a little worse than this.
Basically.
We're gonna have to confiscate that. That,
What was that lamp called?
there you go. Yeah, well. Typical red LED without phosphor. Anybody else? Filter?
To do is put the filter in front of the slit, but with one of those lights that are nasty.
If possible. Let's use the,
This is supposed to be a light pollution filter.
okay. Go ahead and. That there, if you can hold that in front of you, but. Not too bright, but let's take a look. Okay. Get a little brighter than that if you can. Okay. There you go. That's interesting.
How about the RGB phosphorus?
How about without the filter there, what does this do?
Oh, yeah.
It's probably gonna be right, but let's see. I'm sorry. Get a little brighter than that if you would. Oh, way too bright. Oops. Okay, that'll work.
Filter does something, but.
That doesn't look right. So I thought we looked at that one before, that was better. Get it a little higher. Yeah, well, no, I mean straighter in. Okay. Okay, interesting.
So the previous one, which should have a filter in it.
Yeah, I just have these live, so, you know, I can't readily pull them back up.
Oh,
I mean, I could, but they'll
Okay.
slow things down.
okay,
About a
so-
cell phone screen, the RGB phosphorus.
Okay, turn this off. Yep.
No problem.
Got it.
Yep.
Yeah, RGB, all right.
RGB.
Anybody else?
Red light on Sky Guide.
Yeah, this works.
Up closer, bring it closer. Higher. Lift it a little higher. Okay, let me increase the exposure. Okay, you ready? Yep, I'm ready. Hold on. Okay, you're good. You can stand down. There you go. Work.
Turned off all the blue. Turned off all the green.
The red option.
That worked.
See a little bit.
I guess the thing is, it does work after all.
Mhm.
Cuts down on the blue.
Anybody else?
Good for being outside. Doesn't kill your night vision.
All right, well. Great. Does anybody has anything else they want to see? You're welcome to come up and if you have any questions afterwards. And I did mention earlier, I do have, I know Roxanne in her talk mentioned some new gear for occultation planning. I've got some of the new stuff in, so if anybody has any interest in that, happy to show that to you as well.
What about the spectrum on the screen of the other spectrum?
Oh.
It's like the spectrum of the
You're gonna
screen.
make my head explode. Anybody else? Thanks.
All right, any questions? Cool. All right, well, enjoy us for the food in the other room, and join us for the food in the other room, and enjoy, and everybody have a great summer.
Thank you.